Hello, everybody. So, let's see here. So it was a lot of fun for me to be in class on Monday, and I'm glad to have had all the participation. I just, interact with people again. So, there is a homework set that's been uploaded to the coursework page. Okay, you can go and download it there. It's due on Wednesday of next week. We have a periodic table quiz on Monday. In class, you're going to have about 5 minutes to do it at the beginning of class. Sit down and bang it out, and then we can move on to lecture material. So last time we did some periodic table review, and we talked about a couple of concepts. There are quantum numbers that define the types of wave functions you can get. It's kind of like notes in an octave. There are only certain notes that you can have in every octave. The same is true for electron wave functions. And have particular quantum numbers that define them. There's the principal quantum number, then there's angular momentum, and then there's a spin and a magnetic quantum number. And you can't have two electrons with the same quantum numbers fill up an electron shell. So only one electron per quantum number. And then electrons fill up those shells according to Hund's rule. Right? Hund's rule says that electrons want to be high spin if they can. You can't put two electrons with the same spin in the same orbital, right? Because that disobeys the Pauli principle. So separate orbitals, high spin, that gives you the lowest energy configuration. If you pair the electrons, you have to pay a penalty, and that penalty is to exchange energy. You take the two electrons that are paired and push them into the same orbital, you pay some electron-electron repulsion in the form of a Coulomb energy. Right? So if you want to determine the lowest energy electronic configuration, you account for spin, you account for Coulombic effects. And later, when we get to more complicated systems, you also have to think about energy level spaces. In a multi-electron atom, electrons shield each other from the nuclear charge. The nucleus has a charge termed by the number of protons, but that charge is felt differently by each electron because some electrons are on top of the nucleus more than others. Smaller principal quantum number, closer to the nucleus. Higher principal quantum number, further from the nucleus. And then the shape of the wave function impacts the nuclear interaction. Which type of orbital has the highest magnitude on the nucleus? It's okay, go ahead. S orbitals penetrate, they have maximum amplitude at the nucleus. Which type of orbital extends furthest from the nucleus? S also. So if you're in the fourth energy level, you have S, P, G, and F. S has this special thing that it gets all the way to the nucleus and it reaches out the furthest. That makes it sort of most interesting from a chemistry perspective. F orbitals are boring. They don't penetrate to the nucleus well, so they're kind of insensitive. They don't reach out from the atom well, so they don't make bonds effectively. So S orbitals are really important. F orbitals, less so. F orbitals become really interesting when talking about photophysics. F orbitals are involved in the light generation mechanism of that light bulb above your head. They don't do a whole lot when it comes to bonding. All right. What's a radial probability distribution?
It's psi squared r squared.
Psi squared r squared is the way that you write it out, and what does that do for you? William?
It's your probability of where you how likely you are to see your electron on the radius of your psi sphere. from your place.
Yeah, it tells you whether you're likely to find an electron at a distance r from the nucleus. And what happens is r goes to 0, so I squared r squared also goes to 0. So you get these curves that have a minimum at the nucleus. So they start at 0, they go up, and they decay as the wave function decays. It's a way to show you where you're likely to find the electron and kind of how big it is. So the s orbital is extensive and it has a lot more intensity probability close to the nucleus than F does. The way of drawing the size of the thing. Okay, so shielding is really important for properties of atoms and molecules. And one of those is ionization energy and effective nuclear charge. One of those properties. So I'm just going to define these things and then we're going to look at a PDF here. So effective nuclear charge is the charge in electron fields, and it takes into account shielding. Okay. Z is the atomic number, the number of protons, but this is Z effective. You take the atomic number and you subtract the shielding parameter. And these shielding parameters, of course, are going to be different for each type of atom. Turns out, as you go across a row in the periodic table from left to right, the effective nuclear charge goes up. And that's because the shielding parameter goes down. Okay? The effective goes up. This causes electronegativity to go up. Okay. So electronegativity is a reflection of the effective nuclear charge. Fluorine is the most electronegative element in the periodic table. The second most is probably oxygen. And then it goes down as you go to the left. And when you finally get over to lithium, you get something that is not very electronegative. That's a consequence of shielding. All right, so there's something else, of course, we talk about in this context. That's the ionization potential. Ionization potential is the minimum energy that you need to remove an electron. Minimum energy needed to remove an electron from an atom in vacuum. So we have an atom, add energy to it. You'll get an electron plus an ion. Gas phase ion. And if you add a lot of energy, more than you need, this electron will have kinetic energy. It'll be flying through space. But at rest in vacuum, sort of the reference potential, that defines the first ionization energy of that atom. Okay, so we're going to take a look at ionization energies here. And I have a handout for you on the website here. Let's see how well this goes. Yes.
For atomic nuclear charge, when going left to right, is it because the atomic number is increasing and the shielding parameter staying the same, or is it the other way around?
Well, it's the shielding parameter change. So p orbitals do not shield the nuclear charge completely. And so the effective nuclear charge increases. So, if you think about it in terms of you've got 5, 6, 7, 8, 9 electrons. You also have 5, 6, 7, 8, 9 protons. Right? So when you add that last electron, you're also adding that last proton. So what charge does it experience? It doesn't experience a 9+ charge.
Yeah, that makes sense.
If you pull one electron off, the thing that you're holding is +1. You bring the electron off. And it doesn't feel +1, it feels something else. And something else it feels is defined by how well the other electrons shield the nuclear charge from that incoming electron.
That makes sense. Thank you so much.
Yeah. Okay, so let's make this thing nice and big. All right, so we have both the ionization energy here for elements in the periodic table, and we have the radius. So we're going to talk about ionization energy first. Everybody see that okay, or should I turn the lights off? Good? Yeah? Okay. I'll stick. All right. All right. So as you go left to right across a row, so this is familiar. Here's lithium to neon. You can see the ionization energy is going up. So that tells you you need to put more energy into the atom to pop an electron off of it. The degree to which that electron is held by the atom is changing. It's much harder to rip an electron off of neon than it is off of lithium. You still have to pay quite a bit of energy. This is 5 electron volts. 5 electron volts will give you a hell of a sunburn. That's the power of a photon. Okay. And lithium still is holding on. It's because it's hard to put a positive charge, separate charges in a vacuum costs you a lot of energy. You go up to neon, that charge that you're leaving behind, and the binding of that electron to that charge is costly. So you go from left to right, and the effective nuclear charge goes up. And the reason that happens is that electrons that are in the same energy level don't screen that charge completely. Okay, so you're adding a proton, you're adding an electron. Each time the charge goes up more and more, the effective charge, because those electrons don't compensate for that positive charge completely. So here is, this is the 2s, 2p series. Here's 3s, 3p, 4s, 5s. They all have kind of similar slope. Here's the transition metal series. They all have similar slopes. And then here are the F elements, a different slope. Yeah.
What are each one of these points? Like each one of these circles that are here, like from lithium to boron, there's like, it goes above boron, there's a point, and then it drops back down to boron, and boron is still.
Each of those points is a different element. So we've got lithium, beryllium, boron.
Okay. It's just not boron. It's the red.
Yeah, that one's not labeled. You know, potassium to zinc. Here's copper. Here's nickel, cobalt, iron, etc. And you see the same sort of trend of going from left to right in any series, right? So it tells you, for instance, that in the transition metal series, when you go from scandium to nickel, the one on the left is kind of like potassium. The one on the right is kind of like fluorine, right? Nickel is electronegative compared to scandium. Lithium and fluorine, there's a huge difference. You know, you mix lithium metal and fluorine gas, and you're going to get a shell out of that. Scandium and nickel will react with each other, but you know. So same trend as you go from left to right. S is more sensitive to changes in Z effective than P, or than D, or than F. So F doesn't really feel, these are all the F orbitals filling up here, doesn't really feel the effective charge change, okay, because they don't penetrate to the nucleus very well. So even though the effective nuclear charge is going up for those guys, their interaction with it is not very strong. Other electrons in the atom will feel that charge increase more than the F elements do. Let's see. The ionization energy also changes as you go from top to bottom, right? So here's 2, the second, third, fourth, and fifth principal quantum numbers filling. And you can see there's a trend downward in ionization energy. It's easier and easier to ionize when you go down. So iodine or iodide gives up an electron much more easily than fluoride does. Tellurium is, telluride's kind of hard to make. It's somewhat reducing. Oxygen is a heck of an electronegative element. You know, it doesn't give up electrons very easily at all. Dioxygen is a very powerful substance. That's why my hair is white. You know, your bodies are fighting against oxidation every single day. Oxygen is a fog and it wants electrons. You go down to tellurium and the opposite is true. It's hard to make tellurium 2 times. All right. Now, it turns out that the Z effective, as you go down a column, actually goes up. This is the inverse of what I just told you about ionization energy. How could that be true?
the principal quantum number is too high, the electrons are going to be further away from the nucleus, so they're going to be shielded a lot more, and the atomic number is not going to be that much of an effect if it's that far away.
The key issue there is the distance the electron is from the nucleus. So in fact, the Z effective increases as you go down. But the energy penalty you pay to remove the electron is kind of a Coulomb energy. And the Coulomb energy is dependent upon the separation. Once they get really far apart, they just don't feel each other anymore. The Coulomb energy is usually small. So as the electron gets bigger and further from the nucleus, it gets easier and easier to ionize. Okay, so
I still don't think I fully understand why the effect goes up when you go down.
it's because the lower principal quantum numbers, thank you for asking that. The lower principal quantum numbers are on top of the nucleus more so. And so those electrons interact more effectively with the nucleus and they shield much better. So as you go down, oxygen to fluorine, the shielding of the nucleus decreases. The electrons are further away, they don't penetrate as well. The charge is building. The nuclear charge is building because the electrons are far. So that charge goes up, and despite that fact, when you look at the ionization energy, it gets easier and easier to remove electrons because those electrons are also far. So the magnitude of the effective charge is determined by how well the electrons are interacting with the nucleus. The other electrons in the atom, if you're adding something to the fourth or the fifth energy level, there are all those other electrons in there getting in the way. And the fourth and the fifth energy level electrons do not feel that charge very much.
I think that makes sense. I'll probably have to look it up later.
Go ahead, David.
But I don't understand. So the effective nuclear charge, doesn't that change based on which electron you're analyzing? For example, in barium, is not the effective nuclear charge of barium on the 1s electron different from the effective nuclear charge of that same barium on a different electron on a 2p?
Each electron will feel a different degree of the Z. Yeah, so each one has a different shielding parameter.
But for the valence electron in barium, the nuclear effective charge is still larger than the one for strontium, for example. Or would it be lower? Because if the ionization energy is going down, wouldn't the effective nuclear charge also have to go down?
So ionization energy is a property that you measure, the first ionization energy of the atom. So whichever electron is most weakly bound is the one that you're measuring in that case. And the ionization energy tracks with the effective nuclear charge if the electrons you're comparing are all from the same energy level and orbital type. Okay, but in these, but in the case of the main group, where we go from the 2s, 2p to 3s, 3p, 4s, 4p, now you're going down in energy, you're changing the energy level. And despite the fact that the effective nuclear charge is going up in those elements, because the 4s and the 4p's do not interact as well with the nucleus, so they don't shield the charge as well. Okay, effective nuclear charge is going up in those elements, those valence electrons. The ionization energy does not match that, because the electrons that you're interested in are the highest energy ones. So they are easily pulled off. They're far away from the nucleus and they don't feel that charge as well.
So the effective charge still goes up.
The effective charge goes up as you go down, but the ionization energy does not track in that case. Ionization energy doesn't track because because you're talking about, it's a Coulomb potential and it depends upon the radius. Does somebody want to go open that window back there? Yes.
Could this be like thought of because the acre square relationship with like a little bit?
Yes.
Like, so it's like that growth of the radius of the electron denominator overpowers the growth of charge in the numerator.
Correct.
Despite you have a larger charge in the numerator, it's still a lower force that it's being become ionized.
That's right. That's correct. So we'll write this stuff out a little bit more clearly. Normally I would hand out a piece of paper. I guess I could have done that today and write these things down. So let's keep going through them and then I'll spell them out on the board without this projector up there. Okay. So important thing to remember, you go from left to right, the electrons are harder to ionize. You go from top to bottom, the electrons are easier to ionize. And from left to right, the increase is the result of poor shielding of the p electrons. And the result is that the effective charge goes up. Those electrons are increasingly more and more tightly bound. And then as you go down, the electrons are becoming larger, further from the nucleus, and they become more easily ionized. Okay, so the elements in the bottom are more electropositive, the elements on the top are more electronegative. Yes.
So if you look at this graph, you see that lighting, for example, is an exception to the trend.
Yeah,
Is that because the exchange energy?
yes, yeah. So let me just finish my thought and then I'll come back to that. Well, maybe it's not necessary. So wisely, Ethan notes that as you go from nitrogen to oxygen, there's this jump. The question is why? And it's because of the electron configuration and the Hund's rule idea, right? When you have, so this is 2s2, 2p3, so you have 3 unpaired electrons here in this case. You add 1 more electron, and now you have to pair them. You don't get the same amount of exchange. And so, or as I should say, when you pull the electron off of oxygen, you gain exchange energy in doing that, right? You create 3 unpaired spins when you pull the electron off here. Here you create 2 unpaired spins from 3. And so it's harder to pull the electron off in this case. In this case, it's a little bit easier because you get all of that exchange. And that's why there's that little blip in the interface here. Let's see. Here's another good one. Yeah, so remind myself when I introduce the others. So we'll talk about this in just a second. All right, so it turns out that, so this is the 3D transition metal series, the 4D transition metal series, and the 5D transition metal series. Anybody notice anything funny about that set? Yeah.
Pretty, I mean, the increase in ionization energy is minimal in between like each row. I think I have an idea, but I'm not sure, right?
Yeah, well, that's a good observation. It's small between 3D and 4D, and looks to me like 5D is actually harder to ionize than 4D. What's the idea?
Because I mean, there are d electrons and d electrons, like the energy difference between like the different orbitals in the d electron series is.
So the reason that they're sort of flat is kind of the same reason I was telling you about the f orbitals, right? F orbitals don't penetrate the nucleus very well, and so they're insensitive to changes in the z effective. Okay, so the slope is really small. They're all sort of the same. Whereas things like S's and P's, they penetrate effectively, and so it's really big slope. F orbitals, it turns out, because they don't penetrate the nucleus well, don't shield the nuclear charge very well. And so as you're going from left to right, the effective nuclear charge is going up a lot in this series. The f orbital elements don't really show you much of that because they don't interact with the nucleus very well. But that effective nuclear charge is going way up. And then when you get over here to the 5D levels, now the d orbitals penetrate relatively effectively, and they feel all of that charge that is built up across this f orbital series. And that makes these electrons actually more tightly bound than these ones. Okay, so these elements, it turns out, when you go to 5D, you get a funny situation. The 5Ds are usually electronegative because of the fact that the f orbital series fills up just before them. So s orbitals shield effective nuclear charge very well. P orbitals less so. D and f orbitals the worst. Yes?
The question is, why is Mercury and radon at the same concentration? Or similar?
Well, I wouldn't have guessed that, but I wouldn't know what I would have guessed. So I'm not sure how to answer your question. I think the relevant thing to say is that as you go, from left to right, it increases. And as you go from helium to neon to argon to krypton to xenon and radon, you can see that the ionization energy goes down. So the fact that mercury and radon fall on top of each other, I don't have a good way to think about why that would be the case. Okay, so let's see here. All right, let's talk atomic radius. This is another phenomenon that's actually related to the same sort of thing. So the radius of an atom depends upon the effective nuclear charge also. If the effective nuclear charge is really high, the electrons are held tightly, the atom shrinks. So the size of the atom reflects that charge. If you have a neutral atom or you have a positively charged ion, you get very different radii. Neutral, negatively charged, very different radii. The more negatively charged it is, the bigger it is. Okay, so as you go from left to right, effective nuclear charge goes up because subsequent electrons don't shield effectively. That charge increases, the atom becomes more electronegative, and the size of the atom becomes smaller. So here's fluorine, it's at the bottom, right? Notice lithium, beryllium, add a second s electron here, the effective nuclear charge is higher, the atom shrinks. There's more electrons, why is it smaller? Right? It's because of shielding. You go from 2s2 to 2s2, 2p1, it's even smaller. That's a charge thing. So effective nuclear charge and radius correlate with each other. Same is true in the transition metal series. You go from left to right, and the atom shrinks. Scandium is larger than nickel. Big differences, really. Scandium is quite a bit larger than nickel. The same is true as you go from yttrium to palladium, and so on. Boron is larger than fluorine. All right, so radius also goes up as you go to higher principal quantum numbers. Right? You add electrons to outer shells, yeah, it gets bigger. And so any main group element, as you go from top to the bottom, it gets larger and larger and larger. One or two exceptions. I'll show you in just a second here. Notice how jumping from chlorine to potassium, there's this massive increase. That's a principal quantum number.
Can I ask a question?
Yeah.
So the principal quantum number is increasing, that means the maximum probability of the electron falls off closer to the nucleus, right? So the radius is shorter. Right, but you're saying that it's getting bigger as the,
As the principal quantum number grows, the electrons get larger and larger. So, 3s electron, 3p electrons, much larger than 2s and 2p. More diffuse, spread out.
but they do fall out sooner, like the maximum probability gets shorter. Or you're saying
It's larger. So if you were to draw the radial probability distributions of those electrons, you would find they extend much further. And that's why the atom is big. I mean, the size of the atom, the nucleus is nothing, right? It's a speck. The electrons are what we're interested in. That's what tells us how big the atoms are. Okay, yes. The 4Ds are larger than the 3Ds. So yttrium to palladium, all of those elements are larger than scandium to nickel. They shrink as you go from left to right. Scandium may be bigger than palladium. But something else happens when you go from 4D to 5D. 4D and 5D, these guys have about the same size. Why is that?
Is it the same reason we were talking about before, where you build up all that extra charge from the F blocks and then it gets attracted closer to?
Correct. Yeah. The f orbital shell that fills really is poor at shielding. So that nuclear charge is really high, and the 5Ds are contracted as a result. So 4Ds and 5Ds are the same size. You're going to get this question in the homework, you're going to get this question on the exam. Please you want to just remember 4D and 5D are the same size. Palladium and platinum are the same size. Zirconium and hafnium are the same size.
So I've heard this effect called the lanthanide contraction before,
Yeah.
but it seems I've understood that previously as meaning the Fs, that the atoms in the F block are smaller, but it actually seems like it's the Fs are within the F block sort of the same size, and the contraction happens when you get to the D block. Is that correct?
I'm not actually entirely sure what the origin of the name is, the etymology of the word. I imagine people also use it to refer to the fact that the atoms are shrinking here, maybe, but I really think that it's about the way that I imagine that word is that the things that come after the F orbitals filling are artificially small.
So the more meaningful effect is the lanthanide's effect on the D block rather than.
Yeah, I think so. Maybe that's because I prefer transition metals to the lanthanides and actinides. I have to ask an actinide chemist how they feel about that.
Yeah.
All right. Let's see. There's one more of these effects. It's kind of cool. The lesser known scandide contraction. What's a scandide contraction? Helps if you know the periodic table. You just heard about the lanthanide contraction, where 5D is smaller than 4D. What's the scandide contraction?
We call something scandium,
Scandide does refer to scandium.
so something to do with that 3D.
3D shell is filling for the first time. And so who does that disproportionately affect in a way that it didn't affect before? It's the main group. So what does it do to the main group? It affects gallium and germanium disproportionately, it turns out. Are they labeled here? They're not. Well, if it disproportionately affects gallium and germanium, they're right here. Gallium and germanium, it turns out, are about the same size and about the same electronegativity as aluminum and silicon. This turns out to be really important for semiconductors. Laser pointers, solid state light bulbs, a lot of light emitting electronic materials are alloys of aluminum and gallium. And it becomes really easy to grow crystals that are mixtures of aluminum and gallium because they're kind of indistinguishable. Normally, gallium would be larger than aluminum, but there's this Scandide contraction thing that happens that shrinks gallium, makes it similar in size to aluminum, makes their electronegativities very similar. Gallium is kind of a cool element because of this, the fact that it falls right after the D block filling. It has an unusually high effective nuclear charge because D orbitals don't shield very well compared to P's. All right.
Why does the D block have this like weird U shape to it instead of just fingers?
You're referring to both of them, I guess.
Yeah, and I guess it's like a little less prominent in the 3D, but it's still kind of.
Yeah, well, there's a big change of going the first set, probably because in the atoms, there's occupation of S and D going on. On the right-hand side, I would guess that probably the number of dots doesn't look quite right. But I would guess that this guy here is cadmium. Is that right? Yeah. And, at the end of the D block, you start filling S's. You're jumping from D to S. I don't have a good answer, honestly. These are also gas phase atom diameters, and I don't know what the ions are like. That's kind of what I'm used to thinking about. Yeah. Okay. So as you see, you can predict a lot about an atom based on understanding effective nuclear charge. And this is an important thing to become familiar with. You go from left to right, electronegativity goes up. You know that, right? That's a consequence of effective nuclear charge. If you go from left to right, what happens to the radius? It goes down, just for the same reasons, right? Atomic charge is going up effectively. The electrons are bound more tightly. The atom shrinks. This happens in the transition metal series. Scandium is bigger than nickel. Boron is bigger than fluorine, even though they have fewer electrons. Now, when you start going down row by row, the atoms are getting bigger and bigger, unless you have an f orbital block that fills before you. Then you have this unusual situation where there's a very big effective nuclear charge because of the really poor shielding of the f orbital elements, or the f orbitals, and that makes the 5Ds about the same size as the 4Ds. The only other tricky thing that you probably will get confused about on your exam, effective nuclear charge actually goes up as you go down. Okay? But ionization energy doesn't track that. And that's because the electrons are further away. And ionization energy is Coulomb energy. It's the energy it takes to primarily, it's also exchanged, but primarily Coulomb energy. And so the separation of the electron and the nucleus determines the magnitude. Okay? The bigger the electron is, the further from the nucleus it is, the easier it is to pull off. Despite the fact that effective nuclear charge goes up as you go down. So there's up-down thing doesn't match in the nucleus. Okay. Who shields the nucleus the best among the orbitals? S orbitals do. F orbitals stink at shielding. Why is that? They don't penetrate. If you know which orbitals penetrate, you can predict shielding. F orbitals don't penetrate, they don't shield.
How does that process work, the whole penetration of the nucleus?
It's just a statement about the shape of the wave function.
Oh,
Right? Penetration thing is just a shape description. The wave function doesn't have very much amplitude at the nucleus compared to D or compared to P, or if you're an s orbital, you're really in good shape. Your wave peaks at the nucleus. That's what I mean by penetration. Yeah? All right. I think since we spent so much time, I'm not going to spell all of that stuff out on the board. And take a look at that handout. Maybe I'll type it out and add it to the handout. Okay, now we're going to do Lewis structures and BSEPR theory. Some people get annoyed with this. I was annoyed when I first learned this. And I was even more annoyed when I got my first problem set back on this topic, because I thought I knew how to draw Lewis structures. And apparently I didn't, according to my teacher. Same thing is going to happen to you unless you follow the instructions I give you very closely. Okay? I'm telling you this so you don't get disappointed after the first problem set. I'm also telling you this because I feel very strongly about drawing things appropriately. It's very important for communication purposes. If you end up with me on your committee in your second year, I will grill you about oxidation states and charges, and if you are not complete in your drawings, I will make sure to give you a hard time about it. It really matters that you draw things with appropriate charge, number of electrons, so that I know what molecule you are showing me. If you draw something that isn't complete, I'm stuck guessing, I can't follow you, I get upset, and then the conversation's out the window, okay? So, draw things completely. We're going to teach you rules for Lewis structure drawings. These are representations of the wave function of the molecule, okay? They are a representation of electronic structure. Inorganic chemists really care about this kind of thing. And I want you guys to be really good at it, okay? So please accept this material humbly and with the desire to be really good at drawing Lewis structures, okay? All right. We'll talk to CPR next. Lewis structures are a method of drawing things that obey the octet rule. Anybody know who's more of a stickler for Lewis structure representations than me in this department? Jeff Harkin. He's really serious. All right. The system of drawing molecules. In accordance with the octet rule. Or the octet rule. The octet rule tells you whether or not your molecule is closed shell. What does that mean? It's when the molecule's valence shell is full, right? No unpaired electrons. All of the valence shell is filled by making covalent bonds. So covalent bonds are made in order to fill the valence shell. Hopefully you can see that. So in the main group, this gives you the octet rule, all right? You take all the valence orbitals, you make sure they have electrons in them. You get 2s2, 2p6 electronic configurations in the end. That gives you an octet. In the transition metal series, there's the 18 electron rule. You fill up a D shell, that's 10, an S and a P shell, that's 18. Okay, so there's the 18 electron rule in the transition metal series because you fill up the D, S, and P. And in the main group, it's just the S and P. All right, so let's take a look at oxygen, polonium. Where's polonium? Well, it's in the same column. Oxygen and polonium are some noble gas core followed by 2s and 4p electrons. So this is equal to 6 valence electrons. Right? And so if you take a sulfur, draw electrons around it like this, you're making a Lewis representation. Lewis representation shows all of the electrons of the valence shell. In the oxygen to polonium column, you have 6. Now, if we want a closed shell molecule, we're missing 2. So the simplest experiment for electron counting purposes is to think of the number of hydrogens it connects to. So for oxygen or sulfur, you get water. This compound, which we recently evacuated campus with. Hydrogen sulfide, terribly smelling molecule that makes people think there's a gas leak. Natural gas doesn't stink, but they add ethane thiol to it. Ethane thiol, everybody can smell at parts per trillion concentrations. So everyone knows that there's a gas leak when you smell thiols. And we spilled about a mil or liter or less of a compound that produces hydrogen sulfide. And if you take that much hydrogen sulfide and dilute it 1 trillion times, you can cover quite a bit of Manhattan. So hydrogen sulfide is a very familiar rotten egg smell. We add hydrogens to make bonds. To fill the valence shell. Okay. So if you look at these hydrogen atoms, they have 2 electrons associated with them in this bond here. So they have a 1s2 sort of configuration by sharing, and that's filled. You have the sulfur atom here. Now it has a 3s to 3p6, and it's filled. Right? The sharing of electrons allows these guys to reach their octet. Nitrogen to bismuth, same story. Double gas core. We have an NS2, NP3 5 valence electrons. Arsenic, those 5 valence electrons. How many hydrogens do we need? 3 to get to A, right? This extremely lethal and smelly substance. Iron sulfide is also quite poisonous. I think it's more so than iron cyanide gas. It's also the smell of rotten eggs when you fart. But quite toxic, actually. So,
A higher concentration, you stop receiving it sweet.
sweet?
Yeah,
Never.
like never.
No.
I felt like when it reaches certain concentration, you just couldn't smell properly. Like at that point.
People become desensitized.
Yeah.
Yeah. But a lot of compounds are like that. I'm not sure about hydrogen sulfide. It's pretty noxious even at low concentration. Arsine, lethal. Phosphine, PH3, was used as a chemical warfare agent in World War I. So the H atoms have a filled shell. Also has a filled shell on arsenic. Everybody's happy. Okay. Now, if you take this molecule, you can count the electrons. You got 2 electrons in each one of these bonds here, and this lone pair. So you have 3 bond pairs plus 1 lone pair. This gives us 8 electrons around that guy. 2 electrons per bond pair, 2 electrons. Now, these bonds here, the straight lines, we're going to call those normal covalent bonds to distinguish them from other kinds of bonds that we'll talk about next. Okay. In a normal covalent bond, each of the 2 electrons are contributed by the elements that make up the interaction. Okay. Arsenic in that structure has what's called the valence. The valence, what's the valence of arsenic in that molecule? Go ahead.
Yeah.
Oh, 5. No. No, I say no because actually people use this word in different ways. But in this class, in the future, I ask that you use valence to refer to the number of electrons that the atom uses to make bonds. Okay. So the valence in this guy is trivalent. Arsenic is trivalent. Valence is 3. Valence is the number of electrons used to make bonds. So we're going to sort of put it as a formula here. Number of electrons in the valence shell minus the number in lone pairs. Okay, so arsenic has 5 electrons. And there are 2 lone pairs. Gives you a balance of 3. So what's a hypervalent molecule? Hyper means more than, right? Hypervalent means more than the number typically used. Some examples here are phosphorus pentafluoride, the winner. This one. I used to think that was a really nasty substance. Pretty inert. Sulfur hexafluoride. A friend of mine had his retina separate from the back of his eye, had to have eye surgery. And they want to reattach the thing. And one of the ways they do it is they inflate your eyes with sulfur hexafluoride. Totally bizarre, but it's pretty inert.
Is that the gas that you can like inhale and will make your voice super low?
Seems reasonable.
Like the opposite of heat.
Yeah, the resonant frequency will depend upon the medium. There's no voice in outer space, right? So something that's heavier, probably very insoluble, which is, I imagine, why they use it. All right, so we've got 5 normal covalent bonds around phosphorus here. 5 bonds, 10 electrons around phosphorus. And here we've got 6 bonds, 12 electrons around sulfur. So the valences of phosphorus and sulfur are more than 8, right? So these drawings violate the octet rule. And you're going to be asked to draw hypervalent compounds on your problem set in a manner that does not violate the octet rule. These would give you the wrong answer. If you draw that, then you'll be docked points. Okay? Those are the instructions. It's annoying because people draw this stuff all the time. I draw hypervalent representations all the time. But you are going to get marked wrong if you do it on the problem set, okay? And it's because I want you to learn to draw structures that do not violate the octet rule. These ones do. Okay. All right, so what is the valence of phosphorus in this structure? Is that a 5? Pentavalent. What is the valence of sulfur in this structure? Hexavalent. Uses all 6 of its electrons to make normal covalent bonds here. Hexavalent. All right, so people used to talk about SPD hybridization schemes in the main group to deal with this. You know, all right, so we make some more bonds. We just need some more orbitals, right? You can't make 6 bonds if you only have 4 orbitals. So you just borrow some orbitals that are the next energy level up. That was the standard interpretation. Calculations say, no, that's not how it works. So we need a different explanation. And so I'm not going to teach you anything about, adding d orbitals to the mix when explaining the hypervalency of the main group. There's another way to handle this stuff. It's called natural resonance theory. And what it does is it says, all right, well, we don't need covalent bonds for everything. What if we just have some ionic, sort of electrostatic kinds of interactions? That's different than needing an orbital. Many interactions in chemistry are not necessarily mediated by a specific orbital, they're just electrostatic. So for this phosphorus now, according to the natural resonance theory, you just add one electrostatic interaction in place of a covalent bond. Now I have 4 normal covalent bonds. This compound is obeying the octet rule and it has 1 electrostatic interaction. Now notice here we've got formal charges which have a circle around them. Those formal charges indicate that the atoms are no longer sharing the electrons in normal covalent bonds. Now, there are 5 bonds in this molecule. 2 of them are unique. There are 2 types. This thing is a trigonal bipyramidal type of a structure. So there's those in the equator and those in the vertical direction. We haven't quite gotten to shapes yet, but we'll ignore those differences for a moment. We'll just say there are 5 bonds in the molecule. There's 1 electrostatic component and 4 covalent components. And because of resonance and symmetry, we can just say you could write this as the electrostatic interaction, these 4 as the covalent ones. And the point is that all the bonds are sort of equivalent and they are mixtures. Okay. So on homework sets, you could write something like 5 of these. By 5 of these, I mean 5 resonance representations. Okay. To indicate that you mean that all these fluorines are essentially equivalent. Yes.
So those angles are 180 degrees. 120, you exchange them in the same structure.
So this is going to annoy you. We're not going to consider shapes when considering these types of resonance vectors. You can, if you want to, but for my purposes in this class, I'm not that worried about that. There will be cases where you do have to consider shapes when doing resonance structures. But typically for this kind of natural resonance stuff, you don't need to worry about it, and we're not gonna knock you off points on that type of a thing. Okay, so for all practical purposes, these 5 bonds are equivalent.
How can you measure, to see if the theory is, that there's just a hypervalent molecule with sp hybridization, that it's, not a correct characterization, and that natural resonance theory would be, what would be the difference in property if there is this ionic resonance?
So you can take a wave function for a molecule, and you can fit it to component orbitals and show that the d orbitals don't matter. Okay, that's how it's done in practice. Regarding like charging and charge distribution and that kind of thing, I can't tell you exactly how they would have argued specifically for these types of electrostatic pictures. But I think that that will also be borne out in the theory.
Another question, in terms of like bond, like, what do you know about these? Do they match up? Okay, in terms of, like, if we're saying that all of these are resonating, does that actually like pan out in the,
Yes.
like actual bond?
Yeah. Yeah, I mean, as I said, this molecule has 3 fluorines in the equatorial plane and 2 that are vertical, and the vertical ones have the same bond distances, and the equatorial plane fluorines have the same bond distances. Yeah, so because of that, people say, these are equivalent. So you can't draw one representation like this and say, this is it. No, because that would imply those 2 are different, and we know they're not. They're indistinguishable. So it's some mixture of resonance forms, and we're going to do a lot of, the molecule doesn't really care how you draw it, right? It has the property of the vertical ones are identical. So our drawings are trying to represent that to the best we can.
So we regard it as an odd, but it's not actually odd, and it's all resonance structures are the same. And I just think of it as this, it's just kind of a bubble punch just floating around.
That's right. The appropriate description of this molecule is a linear combination of 5 resonance depictions. And that means the charge is evenly distributed. And 4 covalent interactions and 1 electrostatic interaction are shared. But electrostatic interactions are bonds. 2 things are bonded by electrostatic interactions. But that's distinct from a normal covalent bond, which means something particular. Okay? It's sort of a semantic distinction, but it's meaningful when trying to draw things in a way that communicates the type of structure you mean. And I want you to be able to draw molecules in a way that communicates the most information, so that people in the audience say, I know exactly what this person is talking about, and I can see that they know what they're talking about. If you don't draw things carefully and rigorously, people say, does this person know what the hell they're telling me? Should I believe them? So let's learn to draw like pros, and then you'll be much more effective, okay? And also, it'll be much easier to understand what the heck is going on when things get hairy. Last question.
Phosphorus or sulfur form the natural resonance structures and nitrogen or oxygen?
Any atom can in principle, but nitrogen and oxygen generally don't form hypervalent structures. There are exceptions, of course. And we'll talk about them. All right. Here at Table Quiz Monday. Download the homework set. It's due Wednesday. The handout is also available on Courseworks, and I will update it with the rules that I talked my way through so that they're written out for you. The current version does not have that detailed information. I saw your email. Yeah, most likely you won't have enough information to do the process until after class. So, yeah, so, you know, you can get started. Let's see how far we get. And if you want to turn the date on Thursday, that's okay. Thursday's okay for you? Good, all right. Yes. Yeah, that would be perfect. And just, we can send it to both. Thank you, actually, and I will follow through with. All right. Don't be afraid to review. I have too much happening in my life. Keep track of everything. I appreciate that. Okay. Tell me your name. You're Abdullah.
Yeah.
Pleased to meet you.
You know, but I might be out of it in this process.
Oh.
My brain is like, what am I doing? I need to breathe.
Best of luck with that.
Thank you.
Yeah, you'll be fine. It gets easier after 2 weeks.
Yeah, just need to wait for it all to fully appear.
Okay.
You were like, I wish we had that meeting before yesterday, because I feel like that meeting.
Yes, please. What is your name?
Yeah.
Okay, I hope to see it still.
Thank you, Professor Owen.
I think a mask makes it hard to hear. So I would say, when Rui, okay, close. It is on the website. I believe it is Tuesday from 4 to 5.
So it's already on the website?
Yes.
Okay.
On the left-hand side, partway down. Or it was fine. I'll check and make sure. The version on here was not very helpful.